Lena Elenchin. She comes to us from Pennsylvania. She got her undergrad degrees both in biochemistry and chemistry at the University of Kutztown, that thriving metropolis in Pennsylvania. She and her horse dog, Daisy, came down from Pennsylvania and has been here in Tennessee for the last 4 or 5 years. She has worked in my group for most of the time she's been here. She took a trip last summer to Campinas, Brazil, and participated in the synchrotron radiation laboratory course and conference that they had there. She's been to the National Synchrotron Light Source many times with my group to collect various X-ray absorption data. She is going to tell us a little bit about how you might make new types of heterogeneous catalysts today. Lena.
Okay, thank you. So before I get started, I kind of wanted to share some pictures from Brazil in hopes that maybe one of you will apply to attend one of these conferences. So this is a picture of the synchrotron light source. It is small compared to some of the light sources in the United States, such as NSLS2, which is in Brookhaven. However, we got to go to the site. I know it looks just like red dirt, kind of the dirt that we see here in Tennessee, but this is actually where they broke ground to make the new synchrotron light source in Brazil, which is expected to be one of the largest in the world. And finally, while I was there, I had the pleasure of meeting a capybara, which in case you don't know, is the largest land rodent in the world. So on our free day, he decided to spend the day with us. Okay, so as Dr. Barnes said, today I'm going to talk to you about the synthesis and characterization of single-site heterogeneous catalysts for selective oxidation. So before we start, what is a catalyst? A catalyst is any substance that alters the rate of reaction without experiencing permanent changes to itself. And they've become important because today more than 80% of all industrial processes utilize catalysts in one or more of their reaction intermediates. And how they work is they bind to the substrate, forming intermediates that have lower energy barriers, the line in pink here, than an uncatalyzed reaction. So there's two main types. We have homogeneous and heterogeneous. So a homogeneous catalyst is in the same phase as the reactants and products. And they have well-defined active sites, so they're highly selective. So that's their main advantage. Unfortunately, though, they are in the same phase as reactants and products, which makes them difficult to reuse or recover once you get the product that you wish. So on the contrary, heterogeneous catalysts are in a separate phase. Typically, they're metals on solid supports, and they're preferred in industry because you are able to separate them from the products easily because they are in a separate phase. Unfortunately, frequently the active site is unknown, so they're not as highly characterized as homogeneous catalysts, which leads to lower selectivity. So if we think about traditional heterogeneous catalysts, they're often metals grafted on solid supports. And the problem with grafting is that you come up with different connectivities. So here we see that we have 3 bonds from the support to our active site, 2 bonds, or 1. So you could have a combination of these different active sites. If you have a combination of active sites, you can lead to different reaction pathways, different mechanisms, and ultimately at lower selectivity. Not only could we have different connectivities, but we can also have different coordinations, where here we see a 6-coordinate versus 4-coordinate. So how are we going to go about avoiding this? So the goal of our research is to develop a general methodology for the synthesis of supported catalysts which are well-defined and single-site. And we want to do this to try and improve selectivity. So what the Barnes group has done is we've developed a targeted methodology for the synthesis of single-site catalysts. And we do this using the building block approach and what we refer to as the method of sequential additions. What we were able to do is we're able to synthesize highly dispersed, isolated, identical cationic metal centers. And we do this with 3 components. So we have a building block, a linking reagent, which is often a high-valent metal chloride or main group chloride, and then a linking reaction, which we'll go into a little bit more detail here in the next few slides. Okay. So first, we have to pick a building block. So the Barnes group uses this octa-trimethyltin spherosilicate, or what we'll refer to as the tin cube. And there's several aspects of the tin cube that make it ideal for a building block. The first being is that it's robust. So it's a silicon in blue on each corner connected by a bridging oxygen, which is approximately 5 angstrom in length. And what that does is that isolates our reacting groups. So on the corners of each of the cube, we have these trimethyl tin groups, which are going to make great leaving groups when we cross-link it with our active site. So the active sites that we typically use are, like I said before, high-valent metal chlorides. Today we're going to focus on titanium, but it can be used with many other metals as shown here. Okay, so how do we do this? So we're going to talk about first-generation catalysts, and basically what we do is this 2-dose strategy. So in the first dose, we take a precursor, in this case, titanium tetrachloride, and we cross-link it with in a limiting amount with excess tin cube. It's very important to keep the tin cube in excess because that means all chlorides on our precursor remain active. So the chlorides are going, the oxophilicity of our titanium is going to react with the trimethyl tin corners on the cube. And if we keep it limiting, we establish one specific connectivity, and what's shown here is a 4-connected or a fully embedded titanium site. So we have 4 connections to our matrix. So then we're going to cross-link with a second cross-linking agent or an inert linker. And this inert linker basically builds the matrix around our titanium site, locking in the position. Okay? So by varying the precursor, we can vary the number of connections to the matrix. So if we use a 2-connected precursor, so we have 2 chlorides, or 3 chlorides, or 4 chlorides, that's actually how we tailor that connectivity to our matrix. So what's important is that these first-generation catalysts are in a tetrahedral geometry. So both 4-connected, 3-connected, and 2-connected. So it's hard to see where a substrate could actually bind on this 4-connected titanium versus the 3-connected or 2-connected that are not bound to that matrix, so you have a more open site. So what if not only do we tailor the connectivity to our matrix, but we alter the geometry around our matrix? So what we've done is we've altered our precursor. So by taking titanium tetrachloride and exposing it to excess pyridine, we come up with a 6-coordinate or pseudo-octahedral precursor. So now we do the same 2-dose strategy, our first dose with our active linker, our second dose with our inert linker, but now the geometry around our titanium active site is 6-coordinate. It's no longer tetrahedral. So if we apply heat and vacuum, we can remove the blocking ligands, but because we have that tin cube and its robust nature, it does not allow the geometry of the titanium to relax back to a tetrahedral or an equilibrium geometry. So this looks great on paper, but we kind of want to, how are we going to characterize this to see if this is what we've actually done? So there's several characterization techniques that we use, and we have to use more than one characterization technique because unlike homogeneous catalysts, it's not as clear. We need to have multiple characterizations to look at each part on its own. So the first that we look at is gravimetric analysis, which basically the number of tin chlorides that we get off is the same number of connections that we have on the titanium. Then we use FTIR to look at the presence or absence of blocking ligands. We use XAS, or X-ray absorption spectroscopy, to look at the coordination of our active site. And we use NMR to look at the volatiles to see what is coming off of our active site and to actually look at the catalysis of our reactions. So the first I'm going to talk about is X-ray absorbance spectroscopy. So again, we said that we have this titanium tetrachloride bis-pyridine precursor. So without getting into great detail, this 3-band signature, or this 3-band pattern with low intensity is a signature absorbance peak for a 6-coordinate molecule. If we look at our actual catalyst, so not just the precursor, but the catalyst embedded in the matrix, we see this same slight 3-band pattern with low intensity. If you look at a tetrahedral molecule, the signature for a tetrahedral molecule is a higher intensity single-band peak, which is shown in red. So here we see that we are able to alter that geometry from a tetrahedral geometry to a 6-coordinate geometry. So we also use FTIR. So the bottom spectrum in blue is this 6-coordinate titanium center with the pyridines bound. Okay, so we apply heat and we see the loss of 3 signature bands. which correspond to Lewis-bound pyridine on our titanium site. So we know that we no longer have pyridine on the site. Okay, so we also looked at X-ray absorption spectroscopy, again, looking at the coordination of our active site. So here, in the initially as synthesized 6-coordinate geometry, we see both features for a titanium oxygen bond and a titanium nitrogen bond. But after applying heat, we only see a titanium oxygen bond. So we were able to remove those pyridine from the titanium. But perhaps the most exciting or the most prominent characterization technique is going to actually be catalysis, because if it doesn't make a difference, if our catalysts aren't more active than the original catalyst, then there's no reason to characterize any further. So 2 reactions that we took a look at were the oxidation of 2,3,6-trimethylphenol to its corresponding benzoquinone, and 2,6-dimethoxyphenol, again, to its corresponding quinone. And the way we do this is using NMR. So we use an internal standard that allows us to actually ratio the phenol and the benzoquinone to the internal standard, which allows us to quantify how many millimoles or the concentration of our product that we're actually getting out. So what we follow is we follow the loss of our aromatic protons in blue and pink of the phenol, and we look for the increase in the ring proton of the benzoquinone, seen here at H. Okay, so in an ideal world, we'd like all of our phenol to go to our corresponding quinone. So phenol is shown in red, so we see the decrease in phenol. And green is our quinone, so we see the increase in product. Blue is the sum of the quinone plus the product. And again, in an ideal world with 100% selectivity, this should stay constant. So we want to know, as first gen, the connectivity, does it make a difference? So some catalysts that we ran, so we had to do some blanks before we could say, okay, let's look at our catalyst. So the first was no catalyst, so just oxidant and our substrate. And we see at about an hour, there's about 3% of our substrate converted. Then we wanted to look at just our platform, so just that tin cube matrix. Is that going to play an effect? So again, at about an hour, we see about a 9% conversion. So once we start adding titanium, the 2 connected, the 3 connected, and the 4 connected, we see that connectivity does seem to make a difference. So the 2 connected has 50% conversion at about 10 minutes, while the 4 connected has 50% conversion at 60 minutes. So our 2 connected is more active than our 4 connected. However, if we look at selectivity, we see that the selectivity of the 2 connected is only about 56% selective, while the 4 connected is 78% selective. Okay? So if we go to a non-equilibrium geometry, are we able to increase the activity of our catalyst site? So again, that the 4C first gen, at about 60 minutes, that's when we have 50% conversion. But if we look at second generation, where we do not have those blocking ligands and we're in a more open geometry, we see that it takes approximately 15 minutes to reach that 50% conversion point with 81.9% selectivity. So here we were able to enhance activity without losing selectivity, which in the literature you typically see as you enhance activity, you also lose selectivity. What I wanted to point out here was that if we take a look at the 2C first generation catalyst, we see that our 4C second generation, so this non-equilibrium geometry, has almost the same activity as that 2C first gen, but our selectivity is greatly enhanced. So in summary, we were able to create 2 different families of catalysts. We have a first generation catalyst that are tetrahedral geometry, and we were able to show that by tailoring that connectivity, we can alter the activity of these catalysts. So 2 connected is faster than 3 connected, which is faster than 4 connected. But then what if we not only tailor the geometry, or tailor the connectivity, but we also tailor that geometry? So we showed that non-equilibrium geometries are faster, more active than tetrahedral geometries, but we do not lose selectivity. So in conclusion, can we selectively tailor connectivity over another? Yes, we can. We were able to establish a rational strategy for designing better catalysts. And then can we selectively alter the geometry around around an active site, which is really quite amazing because we were able to do it because that's not something that you can do in the literature so far. So we were able to alter the geometry of the precursor and imprint that active site to have the same geometry. So today we talked about titanium and we talked about selective oxidation, but what's great about this strategy is it can be used for other metals as well, and then it can be used and expanded on oxidation, there's epoxidation or hydroxylation, or you could go to solid acid catalysis, porous materials, polymerization, or hydrogenation. So with that, I'd like to thank you for your time. I'd like to thank my group for their support, and I would like to thank Dr. Starin for his help with all the NMR characterization that we've done. Anybody have any questions?
Hold them over.
Maybe underneath one, why did you make this black?
Why does it remain
Yeah.
square planar? Oh, because so it may not be perfectly square planar. However, the size of the cube and the way the cube is robust and locked in around the matrix, it doesn't allow the titanium to relax back. So it's the choice of building block that allows us to keep that geometry.
Have you found the polymerization is catalytic?
I have not.
So
I have
next,
not. Yeah, that's kind of where somebody else is going to head. Yeah.
So I'll ask you a question.
Oh no.
So you made a second generation catalyst,
Yes.
right? What else? What were some of the outcomes that could happen in the second gen catalyst? I mean, how did we know that it was going to be better? And that's a trick question.
We did.
You got it right.
Why did we think it was going to be better? So basically, first, we have a more open site. So in the literature, something I didn't get into, they talk about these fully embedded, or those 4 connected catalysts, where you have a titanium-oxygen bond breaking. Unfortunately, if you can visualize one breaking, what's stopping the rest of the molecule from breaking, losing all of those titanium-oxygen bonds and leaching into the reaction and becoming a homogeneous catalyst. So our thought behind one reason for this was, okay, can we still have that 4-coordinate geometry, locking in the matrix, but not losing or not breaking any titanium-oxygen bonds to the surface, allowing for leaching. Second, when we add those blocking ligands, we should elongate our titanium-oxygen bonds, which would allow the titanium to become more active.
Very good. Thank you again.